So before we begin this lecture, we're just going to look at another reaction, a simple reaction mechanism example, similar to the ones we did in the video. And the main goal here is to be able to take a mechanism, identify any reaction intermediates, and then take the mechanism and write the energy diagram for it. And so this is a two-step mechanism. And again, the way we get the overall reaction for a mechanism is we add up the steps. Now remember, for these steps, we're dealing with individual molecules. And so here's step one is as we discussed in an earlier lecture, is a biomolecular step. And the rate law for this would be rate equals K NO squared. And again, the reason we can write the rate law for these steps is we're dealing with individual molecules, not moles. And then for step two, it is also a biomolecular step because you look at the number of reactants, we have 2. So this would be biomolecular rate would equal K into O2 Br2. So those are the individual steps. Now the overall reaction, what you do is you cross out any reaction intermediates or catalysts. And so the difference between a reaction intermediate and a catalyst is a reaction intermediate is produced in one step, consumed in a following step. Whereas a catalyst is consumed in one step and reproduced in a following step, so it doesn't take part or is not consumed in the reaction. And so with that in mind, you'll notice here that N2O2 is produced in step 1, and N2O2 is consumed in step 2. So N2O2 is a reaction intermediate. And so what we have left is the overall reaction. So we have 2NO plus Br2 yields 2NO Br. Again, it's a coincidence that the coefficients of the overall reaction are the same as the order of reaction for the different rate laws. Now, when we're writing the rate law for a mechanism, we have to write it based on the rate determining step, which is the slow step. So again, rate determining step is the slow step in mechanism. And since it's not given to us in this problem, I'm going to assume that the first step is the slow step. And the reason I'm going to assume that the first step is the slow step is you notice in this mechanism, both steps have an arrow pointing one direction. And the slow step is the step we use to write the rate law. And so if we use the first step, we see that the rate law only contains NO. If we had used the second step to write our rate law for this mechanism, you would have seen that there is a reaction intermediate in the rate law. You cannot have a reaction intermediate in the rate law for a reaction. So you would have to substitute it out if you can. If not, that wouldn't be a valid rate law. And since both of these steps have arrows only pointing in one direction, if we assume step 2 was the rate determining step, then the rate law would be insufficient because we would have a reaction intermediate in the rate law. Therefore, step 1 should be the slow step for this mechanism to exist. And since step 1 is the slow step, we write the rate law based on step 1. And when we do that, we notice that there is no reaction intermediate in that rate law. So by classifying step 1 as the slow step, we know that this reaction mechanism is plausible. Now, in most of these, it will identify what the slow step is. Just for this illustration purpose, I went ahead and assigned the slow step so that we can draw the energy diagram. So again, since there are 2 steps in this mechanism, we're going to have 2 activation energies. The one of the activation energy for the slow step would be the highest energy barrier, because the slow step is what kind of inhibits the reaction. So it's going to have to overcome the highest energy barrier to perform the reaction. So whatever your slow step is, that step will have the highest activation energy. So now when we draw our energy diagram, and let's assume that this is an exothermic reaction, we'll assume it's exothermic. And again, the reason I would assume it's exothermic is because the reactants are 2 nitrogen monoxide radicals and Br2, and our product is NOBr, which is a little bit more stable than the reactant. So I would assume in this case that it is exothermic. So we draw our energy diagram. So we have energy on the y-axis. And we have reaction progress on the x-axis. And so now we start with our reactants. Which is 2NO plus Br2. So those are our reactants. The first step is the slow step, so it's going to have the highest activation energy. Then we come down, we form a reaction intermediate, and we go through the second step and then tumble down to the products. So the first activation energy is for step 1. The second activation energy is for step 2. That doesn't look like a 2. Let's see. Step 2. Now again, the way that I know that step 1 is higher in energy than step 2 is because step 1 is the slow step. The slow step is always going to be higher in energy than the other steps. Now in this minimum here, this is where our reaction intermediate would occur. So here we would have a reaction intermediate into O2. So it gets produced in step 1 and then it gets consumed in step 2, and we have our products. Now since it's exothermic, the products are lower than the reactants. And the difference between the activation energy of the forward reaction or the reverse reaction and the forward reaction would give us delta H. So it's the activation energy, the difference in the activation energies give us delta H here. And this is what the energy diagram of this mechanism would look like. So now we're going to be looking at the kinetics of organic reactions, and we're going to be looking at 2 particular types of organic reactions. The first one is called a nucleophilic substitution reaction. So you can imagine that we're going to be substituting one type of group for another group. And then the second type are elimination reactions, where we eliminate one group and replace it with a double bond. And so for the kinetics of organic reactions, we're only going to strictly stay with what are referred to as haloalkanes or alkyl halides. They mean the same thing, it's just 2 different names to describe the same compound. So what does this mean? So alkyl halides or haloalkanes are a hydrocarbon with a halogen attached to it. So R is the hydrocarbon and X is the halogen. So to give you a few examples, this is a haloalkane. So you have your hydrocarbon component here, this is the R, and you have your halogen, X. And since the halogen is attached to a carbon that only has one carbon group attached to it, this is referred to as a primary alkyl halide. Again, it's a primary alkyl halide. We call it a 1 degree alkyl halide because the carbon attached to the halogen only has one carbon attached to it. So this carbon here that I have circled in red only has one carbon group attached to it, so it's a primary alkyl halide. Now we can have secondary alkyl halides, and the reason I'm telling you this is because this is important when we talk about these types of reactions. Certain types of alkyl halides can react and certain ones cannot react. So if we look at a secondary alkyl halide, let me go back to green. So I'll draw the same molecule, but now make it a secondary alkyl halide. So again, this was the primary. Now to make it secondary, what we do is there's going to be two carbon groups off of that one carbon attached to the halogen. So again, let me draw this in a red circle. So this carbon here, it has two groups now, two carbon groups attached to it. And so since it has two carbon groups attached to it, it's called a secondary alkyl halide. And we usually say it's a 2 degree alkyl halide. So see, this carbon that's directly attached to the halogen has two sticks coming off of it, then it's going to be secondary. When the carbon attached to the halogen, directly attached to the halogen, has one stick, whether it's long or short, it's a primary alkyl halide. And then obviously, the next type is when we have three sticks off the alkyl halide. So let me draw the exact same compound again. So this is our starting with. Now we're going to put two sticks off of that carbon attached directly to the halogen. So here again, that carbon attached directly to the halogen. You count now, we have a total of 3 different sticks, or carbon groups, if you want to call it. I like to call them sticks because we're drawing a stick model. So since there are 3 groups, 3 carbon groups attached to that one carbon, which is directly attached to the halogen, this is called a tertiary alkyl halide. And we refer to this as a 3 degree alkyl halide. So we have primary, we have secondary, we have tertiary. Now you may say, well, what about if there's no carbon groups off of that carbon? And that's a good question. So let's say we just have, let me go back to green. We just have a carbon atom attached to the halogen. So here you notice that there are no carbon groups attached to the carbon, which is directly attached to the halogen. And so this has a unique name. It's called a methyl halide. And so for alkyl halides, this is how you determine whether it's primary, secondary, tertiary, or methyl. You look at the carbon that's directly attached to the halogen and you count the number of carbon sticks that are attached to it. If it's just one carbon stick, it is a primary. If it is two carbon sticks, it's a secondary. And the sticks can be different lengths, they don't have to be the same length. And if it's three carbon sticks, it's tertiary. And if there are no carbon sticks, it's methyl. So these are the four different types of alkyl halides we will be using throughout this entire lecture. So again, it's the number of carbon sticks attached to the carbon, which is directly attached to the halogen. So halogens include fluorine, chlorine, bromine, and iodine. And so what we're doing with these alkyl halides is we're substituting something for that halide. And so what we're substituting for that halide is called a nucleophile. And a nucleophile is a species that is attracted to positive charge. So when we remove that halogen from the compound, then the compound gets a positive charge. This nucleophile, which loves positive charge, is attracted to it. And so nucleophiles themselves are electron rich, meaning they have a lot of negative charge. So when the halogen leaves the alkyl halide, you get a compound with a positive charge, and this nucleophile comes and attracts itself to it, and you get a substitution with the nucleophile. And there are two types of nucleophiles. They can be neutral or they can be anionic. And of course, the anionic ones are generally stronger than the neutral ones. So for example, ammonia is an example of a neutral nucleophile, whereas cyanide anion is an example of an ionic nucleophile. So again, nucleophile, very negative. It wants positive charge. So nucleophile means likes positive charge. And so it's searching for positive charge. So a nucleophile is attracted to an electrophile. So electrophile means it loves negative charge. So it's looking for negative charge to attract itself to. And so electrophiles are attracted to species that are electron rich, aka the nucleophile. But itself is positively charged. And the only electrophile we're going to use is what's called the carbocation. So again, this is the only electrophile we're going to use throughout this entire series when we're talking about kinetics of organic reactions. And so a carbocation is what occurs when the halogen leaves the alkyl halide. And so you get a carbon with a positive charge, which is referred to as a carbocation, cation of the carbon. So this carbocation is positive, your nucleophile is negative, they attract, and you get this substitution that occurs. So for example, there are two ways this substitution can occur. As we'll see, it can occur in one step, or it can occur in two steps. So here, for example, we have methyl bromide, and we have the acetate ion. So again, the acetate ion is our nucleophile. The methyl bromide is our alkyl halide. And what happens is we get a substitution reaction. So in kind of in summary, the acetate is attracted to the positive charge of the electrophile, and then the bromine leaves. And so we get this compound and bromide. And the rate for this reaction, or this mechanism, I should say, is biomolecular, because there's two molecules in this reaction mechanism. And since it's biomolecular, we say it's an SN2 reaction. So SN, S means substitution, N means nucleophile, 2 means it's biomolecular. So there are two reactants in the rate law. Now we can also write the mechanism for this, where we take the exact same two reactants, we get this exact same products, but we can write a different mechanism where it's unimolecular. So only one reactant exists in the rate law. And since there's only one reactant, this is referred to as SN1. So S means substitution, N means nucleophile, and 1 means unimolecular molecularity for the rate determining step. SN2 means substitution of a nucleophile. 2 means it's the rate determining step is a biomolecular step. Now you may ask, well, how do we know the difference between whether it's going to be SN1 or SN2? And we're going to talk about that in just a moment. But let me show you the mechanism between the two, just to kind of give you a prequel of what's to come. So let me erase all these markings. So the first one says it's, we have our reactants and products. It says it's biomolecular. So what this biomolecular means is it's a concerted reaction that would happen all at once. So this would be a one-step mechanism. So for SN2, so if we were to write the reaction mechanism for SN2, it would look like this. Step 1. So if it's SN2, it's a one-step mechanism, and then we get the rate is K minus. So that would be the mechanism for an SN2. It's just a one-step mechanism. And notice that the rate law has no reaction intermediates. Now, if we were to say, hey, let's do this based on SN1, and again, we're going to learn in a little bit why it can only be one or the other, and we'll look at the characteristics of each, but let's just say it's SN1. So SN1 is the rate determining step is unimolecular. So again, SN2, only one step in the mechanism. The rate law is biomolecular. Now for SN1, it's actually going to occur in two steps. So again, with SN1, notice that it's done in 2 steps, whereas SN2 was done in 1 step. And for SN1, step 1 is always, that's in caps, always the slow step. And so the rates law would be this. Now, the reaction diagram would look something like this. So for SN2, and these are all exothermic, for SN2, it would look like that. There's only one hump because there's only one step. For SN1, it would look like that. There would be 2 humps because there's 2 steps, and the first step is always the one with highest energy. And so again, in a little bit, we're going to talk about when we have a methyl halide, does it prefer SN1 or SN2 versus when we have a tertiary alkyl halide, does it prefer SN1 or SN2? Regardless of what alkyl halide you use, it always goes through. If it's SN2, it's always 1 step. If it's SN1, it's always 2 steps, regardless of the nucleophile or the alkyl halide. So you're going to have either one of these mechanisms in either one of these energy diagrams. So just to make a brief clarification, with the methyl bromide, I just showed what it would be for an SN1 mechanism and an SN2. But as we'll learn in a little bit, methyl bromide would prefer the SN2 over the SN1 because this carbocation, as we'll see in a little bit, is very unstable. And so for methyl bromide, it would prefer this one versus the SN2. And so that's what we're going to look at next is how do we know what type of alkyl halide would prefer SN1 or SN2. So nucleophiles, there are a variety of nucleophiles. So we have our neutral nucleophiles, which are things like water, ammonia, amines, alcohols, carboxylic acids, etc. So all of those are different types of neutral nucleophiles. Now charged nucleophiles can be what we call RO-, which is referred to as alkoxides. Right, these are actually called alkoxides. We have, different types of anions involving amines. HS- is a very strong nucleophile, just like hydroxide. We also have what are called carboxylates. That's what this one is referred to as. And they have different varying of strengths. Cyanide is a good charged nucleophile. And based on their varying strengths, as we move on, when we talk about elimination on the next lecture, you see some of these prefer substitution, some will prefer elimination based on the strength. And so charged nucleophiles, very electron rich, can do the substitution. Neutral nucleophiles have to have a lone pair of electrons accessible for the substitution to occur. So for an SN1 reaction, and please pay attention here, this is very important for an SN1 reaction. As I shown you earlier, it's going to be a 2-step mechanism, and that's always 2 steps. The first step, we form the carbocations. That means the halogen leaves the alkyl halide, forming a carbocation. So for example, That's always the first step. The second step, the nucleophile attacks the carbocation. This is why it's called a nucleophilic substitution. You're substituting a better nucleophile for the halide. Now, these are the two steps, the same two steps, regardless of what alkyl halide, regardless of what nucleophile, it's always these two steps. Now, one thing to remember is that primary alkyl halides, that's the alkyl halides with one carbon group attached to the carbon, which is directly attached to the halogen, and methyl halides generally do not undergo SN1 reactions. And the reason they don't undergo SN1 reactions is because of the stability of the carbocation. So as you increase what is called steric hindrance, the bulkiness of the alkyl halide, you increase its reactivity. So don't pay attention to that. That's not what this is doing. And so when you form that carbocation, the carbocation has to be stable. And so for primary and methyl halides, the carbocation is not stable, so they would not undergo an SN1 reaction. Only secondary alkyl halides and tertiary alkyl halides would undergo SN1 reactions because they form stable reaction intermediates. So again, secondary and tertiary alkyl halides would undergo SN1 reaction mechanism. So if you see a secondary or tertiary alkyl halide, the mechanism you're going to write for it is a two-step mechanism. In the first step, you form the carbocation. In the second step, you have the nucleophilic substitution. So if I was to draw an example of a secondary, so that's a secondary alkyl halide. Notice that there are two sticks to the carbon that is attached directly to the halogen, and a tertiary would be like this. It has three sticks attached to the carbon that is directly attached to the halide. And so these types of alkyl halides will only undergo SN1 reaction mechanisms. And the reason is because they form very stable alkyl carbocations. Which are the reaction intermediates. So since they form very stable carbocations, they can undergo SN1 reactions. So the more substituted your alkyl halide is, the more reactive it's going to be. So a tertiary alkyl halide would be more reactive than a secondary alkyl halide. So just to show you some of the characteristics of an SN1 reaction. So here we have a tertiary alkyl halide. Notice that there are three carbon groups attached to the carbon, which is directly attached to the halide. So if you were to draw this, it would look like this. So notice there are 3 sticks. We're going to use the anion acetate, which is our nucleophile. So it's electron rich. And so this is SN1. It's going to have 2 steps. So notice the first step has the highest activation energy because it's always the slow step. So in the first step, what we're doing is this carbon-bromine bond is elongating in the transition state. Then when we get to the intermediate, we form the carbocation. After we form the carbocation, the nucleophile attacks the carbocation, and we start to form this carbon-oxygen bond, and then we get our substitution product. Now for SN1 and SN2 reactions, these are generally going to be exothermic reactions. And the reason they're going to be exothermic is because the carbon-bromine bond is a very, I would say it's a non-polar bond. If it had any polarity, it's very little. So we're replacing a non-polar bond with a carbon-oxygen bond, which is more polar. So we're substituting a non-polar bond for a polar bond. That's going to make it more stable. It's going to be exothermic. So generally with your substitution reactions, these are exothermic because you're replacing a non-polar bond with a polar bond. And notice that there are 2 activation energies for each step. So the first step, we form our carbocation, which is our reaction intermediate. The second step, we have the nucleophilic attack, and then we form our product. Well, on that note, we'll finish the lecture on SN1, and the next lecture we'll talk about SN2 and its characteristics.